Today, we're going to cover vectors. Now, the thing about vectors is the math behind solving a lot of vector problems are really easy. It's just a lot of them to remember. So you'll see like each individual one, it's like, oh, okay, that's not too bad, but it's just a big collection of them. So hopefully few of them, once you see them, it's not really something to remember. It'll kind of click a little bit faster than others. And some of the other ones you have to kind of practice them a little bit. All right, so with a vector, let's say to explain what a vector is, let's say you have your x and your y. Kind of shorten that up a little bit. Don't need that much room. Kind of separate that. Okay, so let's say if we have just our regular line segment going from 0, 0 to some x comma y. Okay. Now this is just a basic line segment. And in a Cartesian plane. Or basically just staying on an xy axis. Just a basic line segment. Just cut off between there and there. The difference between a line segment and a vector, x and y, so let's say you're still starting at 0, 0, but you have an arrow at the end going to some point, we'll call that point P. Q. And we'll call that our terminal point. And where we started, we'll call that P, and that'll be our initial point. Okay. So from P to Q, that's a directed line segment. It has an actual direction. Okay. Now with the regular line segment, you can figure out the length by just making it a right triangle and using the formula for right triangle. For here, the actual length kind of looks like the absolute value symbol. Okay. So that is the magnitude, which is just another way to say the length of the directed line segment. Okay. Now another difference is, other than just the fact that one's directed and one's not, is the fact that with this point here, there's only one x comma y. If you move this line segment anywhere else, then this particular x comma y is no longer a solution. With a directed line segment, let's see if we have our x and we have our y-axis. Uh-oh, I already put the x there. Let's say if you have your line segment here. You can move that line segment there. Or you can move that line segment there. Or you can move it there. As long as it has the same direction and the exact same magnitude or the length, they're all equivalent vectors. So no matter where you shift it around, all of these are equivalent vectors. That's assuming they're all the same length. Okay, so the set of all directed line segments bless you.
Thank you.
That are equivalent to the line segment from P to Q is a vector in a plane, or in the plane. Okay, where these are all equivalent line segments. Bring that up a little bit. All right, so any questions on that so far? All right, leave that up for a few seconds. All right. Okay, so what if we let V with a little arrow on top of it represent the vector whose initial point is at the origin, and whose terminal point is, we'll call it V1 and V2. Okay. Well, this is just the first component and the second component. Okay. So how we're going to write that vector is, that vector is now equal to, so instead of parentheses, we're going to have like these sharp-edged brackets. So we have V1, comma V2. Okay, so we know that, kind of clear that up, where if you have these brackets here, those represent vectors. Where if you have just the parentheses, those represent a point on a line segment. Okay, so that's just a regular ordinary point. So when you're describing a vector, you have to use those kind of sharp edge. I'm trying to think of what they're called, but those little sharp edge corner thingies. They're not brackets, but those little shapes. Okay. All right, so now we're going to look at adding and subtracting vectors. Oops. Okay. And this is one of those things where it's not hard, but there are just so many of them, you have to really practice them to make sure you understand them. So let's say if we let the vector u have components u1 and u number 2. Some books use a and b, some use x and y, but I just use u1 and u2. And we'll let vector v, the components in v, we'll let that be v1 and v2. Clean that up a little bit. Okay, so if we wanted to add these two together, vector u plus vector v all you have to do is add the first components and then add the second components. Okay, so that's how you just add the vectors together. Same thing with subtraction. To subtract two vectors, you get the first component minus the component of the first component of the v, and then you do the second component minus the second component of the v. Right, so let's say for our first example, what if we let u, our u vector, equal 7, 6, and our v vector equal 4, 6. And we want to find u plus v. Okay, so we know that our u is 7, 6, and our v vector is 4, 6. That just means this is our u1, this is our second component, this is our first component of v, and our second component of v. Okay. So we know that u vector plus v vector is just equal to u1 plus v1 and u2 plus v2. So that's just going to equal 7 plus 4 and 6 plus 6. So u plus v is just 11, 12. Okay. So in cases of well, you're not going to do it here, but in cases of three-dimensional vectors, you add the first two components, then the second two components, then the third two components. All right. So any questions on that one? All right. So let's say if we wanted to subtract. Okay, let's say if we let u vector equal -7, -2, and our vector v is -7, -1. And we want to find u minus v. Well, u vector minus v vector. Okay, so once again, we know our u1 and u2. So our u vector is -7, -2. Our v vector is -7, -1. That's our first component of u, and that's our second component of u. This will be our first component of v, and that's our second component of our v vector. Okay, so we do the same thing we did when we were adding, but now we're subtracting. So u vector minus v vector. Remember, that's first component minus the first component of v. You have the second component minus the second component of v. Okay. So that's going to equal -7 minus -7. You have -2 minus -1. Okay, so you have 7 plus 7, which is 0. You have -2 plus 1, which is -1. All right, so any questions on that one? All right, leave that up for a few seconds. All right. Okay, so now we're going to look at scalar multiples. Okay, so if we have the scalar multiple and we'll say some constant c of a vector v is, so if we have some constant times the vector v, that's just that constant times the first component and the second component. Okay, so all you have to do is multiply each component by that constant. So that constant times the first component and that constant times the second component. So it's pretty similar to just the distributive property, where that constant just gets distributed to both. Okay, so let's say, for example, if we know that vector v is equal to 2, 7, find 3 times vector v. Okay, so 3 times vector v is just equal to 3 times the vector with components 2 and 7. Clean that up a little bit. Okay, which means that once you kind of distribute that, you have 3 times 2, which is 6, and 3 times 7, which is 21. So that would be your answer there. All right. Any questions on that so far? All right. Okay, so let's say if we have the example if u vector is equal to -4, -2, and our w vector is equal to -6, -12, find 2 times the u vector plus 1/6 the w vector. Now the variables they use are just variables, just like with regular x and y. They could vary from x vector, y vector, u vector, v vector. Doesn't mean a thing, just the particular name of it. Okay, so the first thing we want to do is find our 2u. So 2 times the u vector, that's just 2 times the vector with components -4 and -2. Okay, so 2 times -4 is -8. 2 times -2 is -4. Okay, so now we find our 1/6 times the w vector. 1/6 times the w vector is just 1/6 times the vector with components -6 and -12. So again, if we distribute that to both, 1/6 times -6 is -1, and 1/6 times -12 is -2. Okay, so we have both term vectors. So now we just add them together. So 2 times the u vector plus 1/6 times the w vector is equal to -8, -4, plus -1, -2. Okay. So remember, when you're adding your vectors, you're going to add the first components. So you have -8 plus -1. You have -4 plus -2. Okay, which will equal -9, -6. It's kind of a combination of all three of those properties. Well, 2 of those properties. We didn't do the minus. All right, so any questions on that one? All right. Right. So we'll do one more quick example of this one. So if we know that our v vector is equal to, we'll have the components 12 and -12, and our w vector has the components 1 and 5. I want to find 1/3 times the v vector plus 4 times the w vector. Okay, so the first thing we want to do is find our 1/3 times the v vector. Okay, so that's going to equal 1/3 times the vector with components 12 and -12. So if we distribute our scalar multiple, we end up with vector with 4 and -4 as your components. Okay, so now we do the second term. 4 times the w vector is going to equal 4 times the vector with components 1 and 5. Which gives us the vector with components 4, and 4 times 5 is 20. Okay. So now we just add them together. So 1/3 the v vector plus 4 times the w vector is just going to equal 4 -4 plus 4 20. Okay, so when we're adding vectors, we add our first components. that'll be 4 plus 4. And we add our second components. Negative 4 plus 20. Okay, so that's going to give us the vector 8, well, vector with components 8 and 16. All right, so any questions on that one? Okay. Looks like everyone's done. Okay, so now we have the vector equations. We're going to look at now how that translates graphically. So vectors graphically. Okay, so vectors are added by connecting their initial and terminal points. Okay, so for example, let's say this is vector u. Okay, and this, we'll let that be vector v. Okay, then vector u plus vector v, you can find that by just connecting the endpoint or the terminal point of u to the initial point of v. So that would be vector u. Try to draw it as close to it as possible. And vector v just connects right to the endpoint. So this line right here becomes our u plus v. Bring that down a little bit. Vector u plus vector v. And it's the same thing if we switched it around. So if we have vector v plus vector u, that would just be vector v, which is that's our vector v. And our vector u, remember that just kind of shifts right on down there. So same direction. Oops, sorry about that, I put in the wrong point there. That's vector u. So this is v plus u, which is really the exact same as u plus v. All right, so any questions on that one? All right. And the scalar multiple literally just expands the scale of the vector. Well, expands or decreases. It depends on what you're multiplying it by. Change the scale of the vectors. Okay, so if we have, let's say we'll make this vector v.